অন্য আমাদের এখনো সিএনপি ভরা আছে কত 1806 1856
1868
1868 আছে।
All right then. Good evening. So today I am going to discuss about the fifth lecture of the transition metal organometallic chemistry principles to applications class. So in this lecture, I have actually summarized the basic principle via some basic concept clearing questions. So through which you will understand the today's topic is regarding the CC and CH activation with the aid of transition metal complexes. So I have designed some questions and I will go through it one by one so that you can have a basic idea on this. So let's start. This is the first question. Is the challenge of CC bond activation arises from one, the inaccessibility of the CC bonds, the less abundant nature of the CC bonds as compared to the CH bonds, the difficulty in forming the initial pre-complex with transitional metals, and the fourth option is the highly reactive nature of the CC bond. So first of all, I would I would one by one discuss about each of the points. The first point is the inaccessibility of the CC bonds. The CC bonds are actually sterically more hindered than the CH bonds because you can see the size of the carbon atom is much greater than that of the hydrogen atom. And to activate CH bond, it is sterically less hindered, but CC bonds are sterically more hindered, and that's why because the other groups are also attached to carbon, the R group, alkyl groups, or phenyl groups, or other groups, because carbons are tetrahedral or planar or linear in nature. Because of the presence of other groups, the sp3 carbons bound to three different groups or same groups. That's why they are actually less accessible than the CH bonds. Secondly, the less abundant nature of the CC bonds. Like for one carbon is actually bonded to three hydrogen atoms at most, because the other carbon is actually bound to one carbon atom. So for one CC bond we are actually having three CH bonds. So you can have a note, so basically you can think like that: for one CC bond we are having three CH bonds, so CH bonds are more abundant in nature. That's why in a lump sum or in a base in a sample of bonds, the CH bonds are outnumbering the CC bonds. That's why CC bonds are less abundant in nature as compared to the CH bonds. The difficulty in forming the initial pre-complex with the transition metals. And the fourth option is the highly reactive nature of the CC bonds. Firstly, CC bonds are, frankly speaking, non-polar or very less polar in nature, because two the atoms are actually homonuclear, and that's why there is no generation of polarity in the CC bond. That's why the CC bonds are very much less reactive in nature. You see, the bonds that are actually polar in nature, that's the HX bond, where X is halogen like chlorine, bromine, iodine, fluorine. When the bond is CCl bond, like or CO bond or CN bond, such kinds of, or SN bond, such kind of bonds have a difference in electronegativity between the two atoms. So homonuclear bonds are actually less reactive. Not only CC bonds, any homonuclear bond you can undertake, like CC bonds or HH bond. So these bonds are actually very much stable in nature because the two of the nuclears that are attached to one another actually same. They are homonuclear, and the pi overlap, or the orbital overlap between the two atoms is much higher in the case of the homonuclear CC bonds. But in case of the heteronuclear polar bonds, the reactivity increases. Now, since CC bond is a homonuclear bond and both the carbon have same electronegativity, that is 2.5, around 2.4 to 2.5 in Pauling scale, that's why these bonds are actually less reactive in nature. So the last option, that is the highly reactive nature of the CC bonds, is actually not true. And lastly, I will discuss about the third point, that is the difficulty in forming the initial pre-complex with the transition metals. I have already discussed that CC bonds are actually very much less polar in nature, or actually non-polar in nature. That's why they are actually very stable, and that's why they are stable by breaking such CC bond and having a initial p-complex with the transitional metals. The transitional metals are actually designed as TM, demonstrated as TM. Now TM is to get bound to CC. TM actually has to induce the polarity on the CC bond, and it is very difficult for transitional metals to actually initiate a difference in polarity in the so-called non-polar CC bond and induce the formation of a pre-complex with the transition metals. That's why there is a difficulty in forming the initial pre-complex with the transition metals. So the options 1, 2, and 3, the inaccessibility of the CC bonds, the less abundant nature of the CC bonds, and lastly, the difficulty in formation of the initial pre-complex with the transition metals, these three options are correct. These are the actually main challenges that we face regarding activation of the CC bond. But the last option, that is the highly reactive nature of the CC bond, is actually not true because CC bonds are comparatively less reactive in nature. So we'll jump to the second question. So here you can see I have actually stated one information, like the CH bonds and HH bonds, they are actually stronger. They are actually 10 kilocalorie per mole stronger than the CC bonds. But statistically, I have already told you, like CH bonds outnumber CC bonds because for one CC bond we are having 3 CH bonds. So the activation of CC bonds is actually more difficult. So it's a second question. The second question is regarding the CC bonds in a transitional metal S alkane. S you can term as sigma and P you can term as pi. So the question is, the CC bonds in a transition metal sigma alkane complex is weakened by ligand to metal P or pi donation, ligand to metal S or sigma donation, metal to ligand P back donation or pi back donation, or metal to ligand S donation or sigma donation. Now the options 2 and 3 are actually correct because the option 2 is the ligand to metal sigma donation. If I am stating the question is framed as it is a transition metal sigma alkane complex, so by default it is actually accepted like this sigma alkane complex will throw some of the electron density to the transition metal. So the first option is the ligand to metal sigma donation. Now, since this sigma bond electron is actually residing in the sigma bonding orbital of the CC bond, and it is actually getting the number of the electron is actually getting thrown upon into a transition metal orbital. That's why, and since from bonding orbital the number of electrons is decreasing, the amount of electron density is decreasing. That's why we know, like if from the bonding orbital the number of electron is actually decreased, then it is an anti-bonding kind of interaction. The bond order gets decreased. So the bond order gets decreased. That's why it is weakened. And the third option is the metal to ligand pi back donation. Now, if the metal is actually throwing back the electron to the ligand is a sigma alkane ligand. So the orbital that it will accept the electron from the metal is the LUMO sigma star. That is the sigma star LUMO. That is the anti-bonding orbital LUMO, where it accepts the electron. Now, if the LUMO electron density gets increased, you should know that from the HOMO, if the electron density is decreased, then it is weakening of the bond or bond order decreasement. And if the electron density is increasing in the LUMO, that also actually decreases the bond order of the bond. So the bond gets weakened. That's why in both the cases, from the ligand to metal sigma donation, from the homo sigma, and from the metal to ligand pi back donation, that is the sigma star on the sigma star LUMO, the back donation is happening. That's why the bond order gets decreased. That's why in case of CC bonds in transitional metal sigma alkane complex, the bond gets weakened for these two causes, option 2 and option T. Option 3, ligand to metal sigma donation and metal to ligand pi back donation. Now we will again come to a conceptual question, that is, a CC bond activation is often achieved via which of the following pathways. So the first option is by the easy formation of the initial transition metal precomplex, by the release of ring strain upon CC activation, by performing the CC bond activation at low temperature, and last option is for the aliphatic substituents only. The correct option is option 2, that is by the release of ring strain upon CC activation. All right. All right. This is a third question. That is regarding the CC bond activation is often achieved by which of the following pathways? By the easy formation of the initial transition metal precomplex, by the release of ring strain, by performing the CC bond activation at lower temperature, or for aliphatic substituents only. Now the correct option is option 2, that is by the release of ring strain upon CC activation. So why this is so, I will discuss. So by the easy formation, I have already discussed this fact that by the easy formation of the initial transition metal precomplex is actually not happening in case of CC bond, because I have already told or discussed in the first and second slide that transition metal precomplex formation initially with the CC bond is actually quite difficult. So the first option is not correct. For aliphatic substituents also, regarding aliphatic substituents contain only CC and CH bonds in a long chain or small chain manner, their activation is actually not even that much facile. In case of option 3, if we conduct the CC bond activation at low temperature, I have already discussed that CC bond activation is actually not that much favorable. Now, for favoring a reaction, we have to perform the reaction at a comparatively higher temperature, because the activation energy is quite high. If a reaction is actually, or activation energy is quite high, that's why we can actually perform, because the reaction is quite difficult. So if we perform the reaction at a comparatively lower temperature, then the activation will be even slower. So at lower temperature, the CC bond activation is not going to get happen. But the second option is actually correct, because it says by the release of ring strain upon CC activation. We know like carbon has catenation properties, and it can form several kind of rings, like 3-member rings, 4, 5, 6, 7-member rings, etc., etc. And the 3 or 4-member rings are actually unstable because they are actually undergoing a ring strain. Now if we are conducting a CC activation so that the bond gets cleaved, and from ring 4 we are going to ring expansion, we are going to ring 5 or ring 6, then the CC activation is actually quite favorable, because it can produce a comparatively stable ring, and the molecule that is suffering from several ring strain will be relieved. That's why by the release of ring strain upon CC activation, the activation CC bond activation can be achieved. That's why in some 4 or 3-member rings, actually the CC bond activation takes place quite favorably, rather than the other 6 or 7-member or acyclic CC rings. So now I will actually discuss about some basic problems of the regarding the CC bond activation reactions. So the first one is this one. This is a predict the formation of the product of the following reaction when this pyro compound, you see, when this carbon is actually connected by cross manner through some four different carbon atoms, then it is called as pyro compound. So these pyro compounds are actually this. These pyro compounds, when it is treated with iron nonacarbonyl in benzene at 80 degrees Celsius temperature, then what is the product? So I have actually shared what is the reaction. So you see, in the first step, this compound is treated with Fe2CO9. Now, since this is a actually 1,3-butadiene kind of system, which is a 4 electron donor, because you can see there is a there are two pi bonds in this system, and each pi bond is a 2 electron donor. That's why this system is actually 4 electron donor. Now the complex has to undergo in such a arrangement, that's why it can obey the 18 electron rule. Iron 0 system, because carbonyl is a neutral ligand, iron 0 is a D8 system. Now this is a 4 electron donor, so 8 plus 4 is 12, and 3 CO, each CO is donating 2 electrons, so 12 plus 6 is 18 electron. So this compound is an 18 electron system. This complex is the 18 electron system. So from Fe2CO9, by treatment with this 1,3-butadiene pyro compound, we are getting this compound. But since this is a temperature, this is an activation energy, and I have already told for CC activation, we need some higher temperature to break the CC bond, to get it get activated. We need some higher activation energy because the activation barrier is quite high. Had not here been this much of temperature, this reaction would stop here. But here this is a trick, like if you are heating this compound at 80 degrees Celsius in benzene, then what happens? You see here one of the CO molecules gets eliminated. And now, since I have already discussed that the ring strength plays an important role in controlling how the CC bond activation will take place. Now in this case, you see this is pyro compound and both the rings are actually 5-membered. Now what happens here, one of the CC bonds from here is actually gets broken. This is actually the CC bond activation. And now rearrangement of this pi bond in this 1,3-cyclobutadiene pentadiene kind of system is happening. Now what happens in this case, one of the CC bond gets broken, it gets activated in presence of temperature, and now they are actually putting 2 electrons in this moiety, so that from 4 electron it is going to a cyclopentadienyl 6 electron donor system. So from 4 electron it is going to a 6 electron system, which is anionic in nature. You see, this is an aromatic system where there are 6 electrons which are actually resonancing or actually getting delocalized inside the in the 5 carbon atoms. Now it is becoming a 6 electron donor, and this CC bond gets broken. Now this CC bond gets activated, and due to accumulation of the negative charge on the bond, it gets attached to the metal center like this. Now you see how many atoms are there in the ring. The 1, 2, 3, 4, 5, 6. Now there are actually 6 atoms. So ring expansion here takes place. That's why from CC, by the help of CC activation, we are going from a 5-membered to a 6-membered ring. So the release of the ring strength is actually playing an important role in this CC activation. Now you see, this is an iron compound, this is negatively charged, this is also negatively charged. So this is iron 2 plus. So iron 2 plus is a 6 electron donor system because it is 3d6, 4s2 is iron 0, so Fe2 plus is 3d6. Now this is a 6 electron donor, this is a 2 electron donor, and these are actually 4 electron donor. So by adding all this, we are having 6 plus 6 12 plus 4 16 plus 2 18. So from this we're actually reaching an 18 electron system actually. So 18 electron system, the 18 electron product is quite stable in nature. So here for your note, I have actually depicted the CC activation involves formation of aromatic pi electron system, because this ring is aromatic in nature. It is actually obeying the Huckel's law of the 4n plus 2 aromatic system, where n is equal to 1 and 4n plus 2 is equal to 6, and the loss of ring strength. From this Packard system, we are going to a relieved ring strength system. That's why this reaction is happening without this temperature, this reaction would not have occurred or proceeded. So from this we are actually getting this much idea, like for happening of CC activation, release of ring strain is actually playing an important role, and also this aromatic pi electron system formation is another driving force behind the CC activation. So now we will jump to the question number 5. This is actually another question regarding the CC activation. You see, this compound is, there are three actually cyclic members which are actually fused to one another. This is C carbon system, alkane cycloalkane system, where these alkanes are actually fused with each other. When this is treated with this rhodium 1 compound, that is rhodium CO whole to Cl. Rhodium 1 is a, how many electrons are there in rhodium 1? Rhodium 1 is a 9 electron, 4s2 3d7, so 9 electrons. Rhodium 1 is an 8 electron system, so these three are actually 6 electrons, so 8 plus 6 is 14. So this is an 14 electron system, and it is quite unstable and reactive in nature. So what is the product when this compound is treated with this fused cycloalkane molecule? So here is the mechanism of the reaction I have shown. Like when this compound is treated with rhodium 1, I have abbreviated this rhodium CO whole to Cl molecule as rhodium 1. You know, like when rhodium 1, the low valent metal centers, when are treated in CC, they are actually either going to activate the CC bond or going to activate the CH bond. Now, these CC bonds is actually getting activated by the presence of this rhodium 1 by the aid of oxidative addition. You see, from rhodium 1, they are going to rhodium 3. And so this is the product. When the rhodium 1 compound is treated with this CC bond gets cleaved and rhodium gets inserted between these two CC bonds. Now you see there is an beta hydrogen atom, because this is the beta carbon and there are two beta hydrogens. You know, like beta hydrogen elimination is one of the major reactions in the field of organometallic chemistry. So here we are having a two beta hydrogens here and two beta hydrogens here. So one of the hydrogen atoms get attached to this rhodium 1. This gets resonance on this, and these are happening a pi bond in nature, and these bonds get broken. So we are having this rhodium 3 hydride, and there is a presence of pi bond in the system. So with the aid of beta hydride elimination from an fused cycloalkane system, we are going to a cycloalkene system, where one of the carbon is actually bound to the rhodium 3, and it is also a rhodium 3 hydride. Now you see here also, these carbon and these hydrogen are actually very much close in proximity, and this is rhodium 3, and to generate the catalytic cycle again, this rhodium 3 compound undergoes reductive elimination. So from rhodium 3 we are obtaining actually rhodium 1, and this carbon and hydrogen gets attached, and this are getting this compound as a major product in nature. So one of the major questions will be, why from this molecule rhodium 1 will not get eliminated by producing the reductive elimination? Yes, you are right if you are thinking in that way. From this compound also rhodium 1 gets eliminated by consecutive resonance of all these bonds, and by relief of this ring strain. This ring strain is one of the major cause for this compound gets eliminated. So this is the one of the major causes when this compound can also undergo reductive elimination by the formation of this, but this is actually less than 20%. You know why? Because beta hydride elimination reactions are quite facile in nature. That's why before this compound can undergo reductive elimination by forming the again this dialkene compound, relief reading strain compound, this compound actually goes to this pathway. So this pathway is actually more favorable than this one. That's why after performing the beta hydride elimination, this rhodium 3 compound is actually at once getting eliminated as rhodium 1, and we are getting this fused compound. But here this relief of the ring strength is actually playing a major role in performing this reaction. When this is undergoing a beta hydride elimination, all the bonds are shifted between this bond comes here and this bond comes here, and rhodium 3 gets eliminated rhodium 1. That's why this CC bond is broken, and you see no cyclo-fused compound here. So here this is a dialkene compound which is getting produced in a comparatively lower yield, and this is actually a rhodium 1 compound which is actually rhodium 1 compound get eliminated, and this is actually a fused cycloalkene compound which is getting at a higher proportion or higher yield. All right, so now we will come to question number 6. So here this is the question. When this compound, this fused benzene compound is actually treated with platinum PET3 whole 4 in benzene solvent at 120 degrees Celsius temperature, what is the product? So this is the reaction mechanism that I am going to discuss discuss about the formation of the reaction, and this is the thing. So let's start with one by one how we can proceed to answer such questions. So PT-PET3 whole 4, PET3 or this phosphine is a 2 electron donor, platinum is in 0 state, so it is a 10 electron system, and 4 phosphorus atoms donating each 2 electrons, so it is an 18 electron system. Now this 18 electron system at benzene solvent at a comparatively higher temperature, that is 120 degrees Celsius, two PET3 molecules, neutral donors, actually gets eliminated to produce this platinum PET3 whole 2. That's why 2 vacant sites are now actually available for platinum to get accommodated with the ligand. Now this is the organic molecule that is actually put in the reaction. Now this is the CC bond. You see this CC bond and these CC bonds both are actually equivalent in nature. So one of the CC bonds will get activated. Your question will be why these CC bonds will get activated, why not the others? Because the other bonds are actually part of this stable aromatic benzene ring, but these CC bonds are not. And you can see these CC bonds actually forming a cyclobutadiene kind of arrangement, that is 4 electron inside a cyclic system. That is why this is quite unstable in nature, because they are anti-aromatic in nature. That's why this compound will be highly reactive, and this CC bond will be activated in presence of the metal. So metal gets inserted between these CC bonds, and we are having this platinum plus 2 system. This is also an 8 electron system. You can see this CC bond gets activated and platinum gets inserted into between these 2 CC atoms, and now we are getting this. Now again this compound will come. Now this organic compound is actually put in large excess to actually see what is the product. Now this compound will again come, and now it will, these CC bonds will again get activated, and it will be actually in cyclic manner get bound to, and these CC bonds will again be cleaved, just as this CC bond was cleaved. So this CC bond is there, this will again be cleaved in presence of this molecule, and this molecule will again get attached to this CC bond by breakage of this CC. Now this is the, now this compound, you can see here these CC bonds gets activated, and these are bound to these carbon atoms of the benzene ring. Now you can see the platinum is actually anchoring this entire carbon chain. Now what will happen? This is a platinum 2 compound, because here you can see this is an oxidative addition by which platinum is getting bound to the CC bond. Now the only possibility that can happen here is the reductive elimination. Reductive elimination, oxidative addition, this beta hydride elimination or microhydride insertion, these are actually some basic examples or reactions that will be very helpful for you to understand the basic principles of the organometallic chemistry. Now what will happen here? The platinum 2 compound will undergo reductive elimination, and it will give back this catalytically active species platinum 0 PET3 whole 2, and this compound will be produced. Now this is a classic example of CC activation, where removal of anti-aromatic cyclobutadiene pi conjugation will happen. You see from this cyclobutadiene pi conjugation, they are actually producing this, where all the four actually rings are actually aromatic in nature. All the four rings are actually aromatic in nature, because these are actually benzene rings 6 6 6 6. All the rings are actually aromatic in nature. So from cyclobutadiene, it's a 4n electron anti-aromatic system that actually by producing the cyclic benzene system, where these benzene are actually getting placed in the periphery of the molecule, are actually producing this stable molecule. This is a driving force, the removal of anti-aromatic cyclobutadiene pi conjugation. Now let's come to the seventh question. This is the question: what is the predict the formation of the following reaction? What happens when this compound is treated with, firstly, this RHCl PET3 whole 3 at 150 Celsius temperature, and the second option is what happens when this compound is treated with rhodium pH PET3 whole 3, and the second in the second way, in the second step, the reagent is HCl at a comparatively lower temperature, that is minus 30 degrees Celsius, and then they are heating it at 100 degrees Celsius. So what is the product? So this is the reaction. This is a classic example from a renowned scientist Milstein's paper 1999, and where the reaction has been demonstrated to see what is happening. So what happens here? So firstly, this is the molecule. So this is the molecule. You see, these are actually having two Pme2 groups actually getting anchored from this meta position to one another, and we have three methyl groups. And firstly, let's talk about this step. What happens when this compound is treated with RHCl PET3 whole 3? Now, this is actually classic analog of the Wilkinson's catalyst, because Wilkinson's catalyst, you all know, is rhodium Cl PPH3 whole 3. This is actually nothing but rhodium Cl PET3 whole 3 at a higher temperature. So what happens here when RHCl PET3 whole 3 is given at a comparatively higher temperature? This CC bond gets activated. So your question will be, why this CC bond? There are actually several CC bonds here. Why not these CC bonds, but only this CC bond got activated? You see, if these CC bonds got activated, then the rhodium will not get any anchoring atom to get bound to and to satisfy the electron count of it, because the Pme2 groups are actually far from these two methyl groups. But this CME group, the CME bond, is actually residing quite nicely between two anchoring phosphorus groups. That's why when the rhodium atom will get oxidatively added to activate the CC bond, it will get bound to these phosphorus groups and it will get stabilized. Because because by CC activation, the metal is going from a lower to higher oxidation state, and to higher oxidation state, the electron donating property of the ligand is actually stabilizing the metal. That's why this CC bond gets activated. So this RHCl, this RH will get inserted into the CME bond, and we are having this RHME, and the one of the P group will be eliminated or removed, that is the ligand dissociation, and we are obtaining this compound. This compound is actually very stable because it's a pincer compound. This carbon, this phosphorus, and this phosphorus actually binding it quite strongly. It's an octahedral compound, and the P3 Cl minus and the methyl minus are actually the other ligands. Now let's come to the other option. What happens when treated with rhodium pH PET3 whole 3? So here, when they are treating the compound rhodium pH PET3 whole 3, instead of CC activation, CH activation takes place. So your question will be why? In this case, I am saying the CC bond is activated, but in this case, the CH bond is getting activated. So what is the reason? In both the cases, ligand dissociation is one of the prior steps. PET3 elimination is happening, and in this case, the CH bond is activated. Nothing but the actually stability of benzene, because the ligand associated here, it is a phenyl, and here the ligand associated was chloride. So here you have to understand about the bond strength. See here, the rhodium Cl bond is actually much stronger in nature. That's why rhodium is retaining here the Cl bond, and because it's a metal and a halogen, the metal halogen bonds are quite strong in nature because metals are electropositive and halogens are electronegative in nature. That's why the rhodium is actually retaining the Cl bond here and it gets inserted between this Cc bond. But in this case, it's a phenyl, this carbon containing compound, and this phenyl rhodium bond is not that much stable because this is an organometallic compound, and the electronegativity difference, the ionic character of the bond is quite also that much not high as compared to the rhodium Cl bond. In this case, nevertheless, the phenyl H bond, because this is actually having are having 3 CH bonds here because it's a methyl group. Now this phenyl is actually quite prone towards abstracting this one of the hydrogen by activating the CH bond, because you see, because these CH bonds are actually quite stable in nature, they are actually high, there are high bond dissociation energy. So instead of getting inserted between this carbon carbon bond, the phenyl group actually abstracts one of the proton and the rhodium gets attached to the carbon. That's why it is a classical example with the elimination of benzene, because this phenyl minus is abstracting one proton. By elimination of benzene, we are actually getting this organometallic compound rhodium CH2 phenyl, and this is a pincer binding like this one, and the PET3 group is actually treating or eating up the valency of the rhodium. Now, when this compound is treated with HCl at a comparatively lower temperature at minus 30 degrees Celsius, what happens in this case? I have already discussed about the fact that oxidative addition of polar moieties happens in a trans manner, and oxidative addition of less polar or non-polar moieties happens in a cis manner. Now, in this case, since HCl is a polar molecule, it contains a polar bond, this HCl gets oxidatively added between in the rhodium 1 center. That's why we are having rhodium 3 center, where hydride and Cl are actually trans to one another and all the groups are actually same. Now, if they are treating actually heating or putting the activation energy to have at 100 degrees Celsius, what happens? This CH2 minus will abstract this hydride and it will be a methyl. Now again we are actually putting back to the compound which we obtained when we treated the parent compound with RHCl PD3 whole 3. So by this way also we are reaching this, and by this short way, this treating it with RHCl PD3 whole 3, we are actually obtaining this one. By analogy, you can also say like here we are putting RHPH PD3 whole 3. Again we are treating with HCl. That's why the compound that is generating here is actually benzene and RHCl PD3 whole 3. That's why in this case and this stepwise pathway, in both the cases we are obtaining this single compound, that is the octahedral rhodium 3 compound getting oxidatively added in the rhodium 1 center. Now the question else comes to the question number 8. It is regarding comparison between the relative stability of the two compounds. Compound A is CH3CO whole 4 and compound B is CF3CO whole 4. So this is the answer, where a classical example of low stability of low valent metal complexes will be discussed. Now, the compound A is methyl containing and compound B is CF3, that is a trifluoromethyl containing. In both the cases, we have to compare the stability. So here for your information, I have given the actual fact that the CF3CO whole 4, this molecule can be distilled without decomposition. It is quite stable and it is distilled without decomposition at a comparatively elevated temperature, 91 degrees Celsius. But same is not true for compound A, because it readily decomposes at even minus 30 degrees Celsius. It is actually stable below minus 30 degrees Celsius. So why is so? In both the cases, the cobalt compound is actually 1 in oxidation state, and you know that the low valent metal complexes are those where the usual or less than the usual oxidation states is actually present, 0, 1, -1, such kind of cases. So low valent metal complexes are those where the electron density on the metal center is actually quite high. So there are some pi acidic ligands, that is like CO or NO plus or cyanide. These are the ligands which are actually called pi acidic ligands, because they are actually able to pull the electron density from the electron rich metal center. So the electron density on the metal center gets reduced, and that's why the metal complexes get stabilized. So the low valence metal complexes are always stabilized by such pi acidic ligands like CO or cyanide or NO plus, etc. But here you are seeing both the compounds are having 4 CO molecules each. So by the help of CO, we are not going to answer it. The other ancillary ligands are CH3 and CF3. Now in this case, you know the group electronegativity of the trifluoromethyl groups is much high than that of the methyl group, because fluorine is actually is the highest or the most electronegative element in the periodic table, and the CF2 group has a group electronegativity in the range 3.8, almost tending to 4, that is of the F. But in case of methyl, the group electronegativity is quite low, that is only 2.2. So the electron withdrawing inductive effect in case of CF3 is much higher than that of the methyl or the CH3 group. That's why in case of CF3CO whole 4, the metal complex is quite stable in nature. That's why it can easily be distilled without decomposition. But here we can also answer it, the same question in some other way. You know, like the CF3 groups are actually is depicted or abbreviated in the says RF. So RF group is having singly bonded with the metal. Metal is nothing but cobalt here. So because the electronegativity factor plays a major role, and the RF is having a higher electronegativity nature and metal is electropositive in nature, so the sigma bond character of the RF metal bond is quite high. That's why the MC overlap increases with the metal orbital when the higher partial charge is happening on the metal del plus and the higher negative charge is happening in the RF minus. In case of that, the low lying pi star, that is the IRF of MO, will put the electron density on the low lying pi star. That's why it facilitates the metal to air pi back bonding, thereby the increasing the metal C bond strength. So in both the cases, when the fluorine atoms are present, the bonding with the metal atom is actually quite stable in nature. But in case of methyl groups, since the electronegativity factor is not that much happening here or that not much prominent, that's why the higher partial charge on the metal is not getting developed. So the ionic character of the metal carbon bond is not that much. It is more covalent in nature, so the orbital overlap is not that much high. And also in case of the LUMO, that is in case of the when the fluorine molecules are present, F atoms are present, the F atom actually stabilize the metal orbitals through the aid of electronegativity. But in case of methyl group, the low lying pi stars are actually not that much low lying. It's actually quite higher in energy. That's why the metal to the ligand back donation also decreases when the group is methyl or CME3. That's why CF3CO whole 4, this molecule is actually quite higher in stability, and it can easily be distilled without decomposition at a comparatively higher temperature. Same is not true for the case of the methyl analog of cobalt. Here the similar question is actually put, that is what is the which of the following reactions is more favorable. The first reaction says the RMCO whole n, when it is delta is treated with at high temperature, RCO MCO in -1, and when the R group is substituted by RF, that is a fluorine containing methyl group, RF MCO whole n, and by giving a large by treating it at high temperature by thermal energy production, what happens, the RFCO MCO in -1. So which of the following reactions is actually more favorable? So this is the answer. This is a basic question, very much basic question, and that we need to discuss to clear the concept about the migratory insertion and the relative stabilities of the bond of carbon with metal. Now, in case of 1, the reaction actually occurs readily. But in case of B, the reaction takes place rarely and only at elevated temperature, because the delta in this case is quite high than delta in this case. So the hint I have given, that is the higher bond dissociation energy of the RF bond makes CO insertion unfavorable. So you see, this is the reactant, left hand side is the reactant and the right hand side is the product. So the more the product will be stable, the more the reaction will be favorable. The more the reactant is stable, the less the reaction will be favorable. So between RM and RFM bond, like in the previous slide that I have discussed, the RFM bond is quite strong because the bond dissociation energy is quite high. The reason being the RF is actually containing several fluorine atoms. That's why the group electronegativity of RF is quite high. So the del plus charge on the metal is quite high in case of RF M bond, and that's why the ionic character of the RF M bond is more than the character of the RM bond. That's why RF M compounds are actually quite stable than the RM compound. And that's why, since this RFM bond is quite stable, so the breakage of this bond and by insertion of this carbon into the RFM bond is not happening in this case. But in the first case, when RM bond is normal, R is normal methyl group or a CME3 group, it's treated with methyl. So breakage of this C metal bond and insertion of this one of the CO into the CM bond by producing this RCO, that is the acyl intermediate bound to the metal intermediate, is not that much. It is actually quite favorable in nature, because breakage of this bond is actually not that much difficult. But when the R group is substituted by RF, that is fluorine containing groups, then the RF metal bonds are actually quite stable in nature. So this molecule is actually quite reluctant in nature to get broken the bond, and the CO will not get inserted. So one of the representative examples of this concept is when we are treating the compound NaMnCO whole 5 with RFCOCl. So RFCOCl is nothing but we can think RF as CF3COCl, RF as CF3 trifluoromethyl group. So CF3COCl is treated with NaMnCO5. Now Na is actually Na is plus, that is positive in nature, so it will abstract the Cl minus. So one of the product is NaCl. Now MnCO5 minus, it is, I have already told, this is a kind of nucleophilic in nature, because these are metal carbonylate, and metal carbonylates are actually very much stable in nature, and they are actually highly reactive, and they treat as a nucleophile. So this nucleophile will attack on the RF center of the CO and will form this acyl intermediate, that is the RFCO MnCO whole 5. But as I have told, the forward reaction is not favorable. The backward reaction is actually, if the forward reaction is not favorable, the backward reaction is automatically becomes more favorable in nature. So here, since the RF M bond is quite stable, so this molecule will readily get converted into this molecule by the elimination of this CO. So this CO, because this RF M bond is quite stable in nature, so this CO will get eliminated in presence of temperature, and we are having this RF MnCO whole 5. Same will not be the case when we will treat this compound CH3COCl with MnCO5. Then the compound will be CH3CO MnCO whole 5. So here the migratory insertion will be the major product. But here, instead of migratory insertion, the reverse of the migratory insertion, that is the elimination of CO, will happen, and from this acyl fluoroacyl intermediate we are having this RFMN compound. This is another example. So similarly, we should have to explain why the reaction where unexpectedly no product containing a RF-TM bond is produced, where RF is equal to CF3. So likewise, in the previous examples, I have already told the RF metal bonds are quite stable in nature. So in all the cases, you see the RFM, so the reaction will proceed in such a manner that the RFM bond will be a product containing RF metal bond will be happening. So here it is not the case. The reaction is depicted as 2CF3I is getting treated with MnCO whole 5, and it will the reaction the producing Na is MnCO whole 5I with sodium iodide and hexafluoroethane is one of the product. So how this reaction will be is justified, why there is no compound where containing RF-TM bond. So here this is actually case of ampolang. So ampolang is nothing but an abbreviation, a special case for the reversal of polarity. Here you see, if this compound is actually any Ri, where R is a hydrogen containing group and iodine is a electronegative halogen. So this R will be del plus and I will be del minus. But in this case, when the fluorine atoms are getting substituted against hydrogen, this is RF, that is del minus, and I will be del plus. So here, instead of del plus del minus, we are having del minus del plus. So this is actually special case reversal of polarity, that is ampolang in nature. That's why this RF minus is there. You know that sodium is positive and MnCO whole 5 is actually electro negative in nature, that is in minus, that is nucleophilic in nature. So here MnCO whole 5 minus, instead of abstracting this CF3, that should be the positively charged, it is abstracting this I del plus, because MnCO5 is del minus in nature and I is del plus in nature. So MnCO whole 5 I will be there. Now Na plus is actually residing alone, so Na plus will be abstracting this iodide, because this iodine will be then acting, because in presence of sodium, the electropositive metal, it will be acting as del minus. So iodine will be abstracted to produce NaI. Now what happens to the CF3? So in case of the CF3, two CF3 molecules will have no option except to get quantified or actually get attached to one another, and will produce this hexafluoroethane. This is actually in case which favors, this is the RF, the reversal of polarity. The presence of fluorine atoms in the R group is actually favoring the nucleophilic attack of this MnCO whole 5 minus on the I, not on the CF3. So there is no electrophilic attack, so no RFTM bond. So RFTM bond would happen if this Mn minus, this MnCO whole 5 minus would attack on this carbon. But this CF3, this carbon is del minus in nature. So this del minus and this del minus will be repelled. That's why there is no product where RFTM bond is present, except they are getting this MnCO5I and the addition product of these two CF3, the homocoupled product, that is the C2F6. So here that is the question is, write the product of the following reactions. The first option is the CpFeCO whole 2 Na when it is treated with C6F6, and the second question is the when MnCO whole 5 treated with this hexafluorocyclobuta monoene compound. So here's the answer. So I have already told that the metal fluorine bonds are actually metal carbon bonds having the fluorine, the RFM bonds are actually quite stable in nature. That's why we are already having any many of the cases, except the last example, the compounds containing RFTM bonds are produced. So here what happens? This is CpFeCO whole 2 minus Na plus. So this minus will attack on one of the carbon atom to eliminate one of the fluorine atoms. This Na plus will take up one of the fluoride, so it will be NaF. Because of the stability of the sodium fluoride, because it is a very stable ionic compound, NaF gets eliminated, and what happens? There forms a sigma bond between the metal and the RF. This is C6F5 is the RF, that is the pentafluorobenzyl benzene group. So in this case, RFTM compound is actually getting produced. Same is happening in case of options 2, case 2, that is NaMnCO5. The NaMnCO5, what happens? NaMnCO5 can be abbreviated Na del plus, MnCO5 del minus. So here also NaF will be eliminated. Now the question is, in here all the actually fluorine carbon atoms was equivalent, but here the carbon atoms are not equivalent. These carbons, carbons are equivalent, these two carbons are equivalent. The question is, on which of the carbon atoms the Sn2 attack or the nucleophilic attack will take place. So I have already discussed about the Sn1 Sn2. I have actually asked to go through about the Sn1 Sn2 reactions, what happens in this case. So Sn2 reactions happen on the actually sp3 carbons rather than on the sp2 carbons. So these carbons are actually electronegative in nature, but these carbons are actually less electronegative in nature, and there is actually two fluorine atoms are there. So the effective del plus charge on this carbon atom is quite high, but in this case the effective positive charge on the carbon atom is quite less, because it is attached to only one fluorine atom. Here it is attached to two fluorine atoms, and this carbon is sp3 in nature. That's why the percent electronegativity is 25. But in this case the carbon is sp2, that is more electronegative, 33% electronegative character. That's why this carbon is actually less electronegative, that is more electropositive. So MnCO5 minus will attack on this carbon, and one of the fluorine atoms will get eliminated as sodium fluoride, that is NaF, and we are again getting RFTM compound. So in both the cases, because due to the availability of the strong nucleophilic metal carbonylate, this will attack on the carbon, that you have to discuss or have to think on which of the carbon atoms the nucleophilic attack will take place with the concomitant release of sodium fluoride, that is NaF. So this is the last question I have taken here. In this case, we are actually having three reactions. What happens when each of the reactions takes place? One is the RFI is treated with FeCO5. Second option is the C2F4, that is tetrafluoroethylene, is treated with FeCO5. And the last question is C2F4, the again tetrafluoroethylene, is treated with CO2CO8, dicobalt octacarbonyl. So all the metal carbonyls are treated with RFX compounds. All are actually RFs. So this is the answer. So again, one by one, we will discuss what's the product. So in this first case, you see this is a FeCO5, that is iron pentacarbonyl. Now iron pentacarbonyl is an 18 electron system. Now you know, for 18 electron system to get oxidatively added to a substrate, because you see I have already told, when the molecule will be polar, the oxidative addition will take place in a trans manner. So in this case also you see the in the, so the first of all, with the release of the CO, the oxidative addition will take, because 18 electron compound will not undergo oxidative addition, because then it will be a 20 electron compound. So firstly, CO elimination will be the first step. So it will be FeCO4 with release of CO. Now this RFI bond will get oxidatively added to this iron compound to produce this iron plus 2 compound. This is again a iron plus 2 compound of 18 electron, and this iron 2, and RF is you can take up as CF3 or other thing, that is I have told, or C6F5. Second question is C2F4 when gets reacted with the iron pentacarbonyl. So in this case, you see two of the CF2 groups, you see, because the CC bond is actually double bond in nature, and the breakage of double bond by oxidative addition actually that will not be that much feasible where that was in the case of single bond, because double bonds are actually more stable than a single bond. The bond using energy of double bonds will be more. So in this first case, what happens, the cycloaddition will take place between these two CF2 C2F4 molecules. So these C2F2 C2F4 molecules will get cyclically added to one another. Now this release of the CO will happen, and this FeCO4 will get oxidatively added, just as the previous example. So this is again an iron 2 compound having this organic carbon containing organometallic reagent having 8 fluorine atoms and these 4 CO groups. This is actually again an 18 electron system. So last question is the insertion into a metal-metal bond. You see, I have already told, like in this case, the CC bond is actually not broken, but in this case, the cycloaddition takes place. But when the metal is actually cobalt, now cobalt is actually residing in the Irving-Williams series in the lower end. That's why the phi or the ionic potential of cobalt is quite high than that of the iron. So the effect of the or the power or the energy required in getting inserted into a CC bond is in case of this because the CC bond breakage is not that much actually easy, because when I already told the CC bond breakage is not actually easy because it's double bond nature and the fluorine atoms are actually stabilizing this system. So in this case, what happens, instead of getting cyclically added because we are having two CO moieties in this single compound octacarbonyl dicobalt, so one CO4 fragment gets attached to the this carbon, and another actually get attached to the this compound. This is actually insertion into the metal. This is actually get the C2F4. Rather than we will not say this metal will get inserted into the CF2, but this C2F4 molecule is getting inserted into the CO bond. The CO bond had a single bond character before reacting with the C2F4, but in case of C2F4, the C2F4 moiety gets inserted into a C2, the CO double bond, the CO bond. Now the each of the CO is now from 0 it is going to a +1 state, because now it is not an oxidative addition, because oxidative addition produces a more than a, from 1 it will be producing oxidative addition +3. Now from 0 it will be producing +2. Now from 0 we are reaching +1. So this is actually insertion into the metal bond by this RF. This C2F4 molecule will be termed as RF. So this is it. So now I'll ask if any of you have any doubt regarding any of the questions, you can carry on.